In this notebook, I'm going to give demo of deep learning assignment of nonlinear regression variants. This notebook is used to build a three hidden layer neural network for nonlinear regression using synthetic data with three input variables. And these are all the points that I'm going to be doing in this notebook. I'll start with the first code cell. In this first cell, I install the required libraries. I use TensorFlow mainly for tensor operation like tf.einsum, scikit-learn for PCA and train test split, and matplot library for plotting. In the next cell, I import NumPy, Matplot library, train test, split, and PCA. Then I set a random seed so the results are reproducible. After that, I generate synthetic nonlinear regression data using three input variables x1, x2, and x3. The target y is created using a nonlinear equation that includes sign term, polynomial terms, interaction terms, and noise. So this gives me a nonlinear regression data set. Then I combine the three inputs into a future matrix X, reshape the target vector Y, and split the data set into training, validation, and test sets. Finally, I print the shapes of these three variables to confirm that the split is correct. In the next cell, I create a 4D style visualization of the dataset. Since I have three input variables and one target variable, the data is effectively four dimensional. To visualize it, I reduce the three input dimension into three principal component using PCA. Then I create a 3D scatter plot and I use a color to represent the target value. So the 3D position shows the transformed input futures and the color shows the target output. Here we can see PCA1 is on x-axis, PCA2 is on y-axis, PCA3 is on z-axis, and this is the color bar that I was saying which actually represents the target value. We can see target y, and this has been defined here in the input code. Next. In the next cell, I import the TensorFlow and set the TensorFlow random seed for reproducibility. Next is parameter initialization. This is a manual neural network setup, and here I define the architecture. Input size is 3. First hidden layer has 32 neurons, second hidden layer 24 neurons, third hidden as 16 neurons, and output size is 1 for regression. Then I manually initialize the weights and biases for every layer. This is important because in this notebook I am not using built-in high-level model classes. I am explicitly creating all parameters by myself. Next, in this cell I define activation functions and its derivative. Next, forward pass. And in the forward pass, I define the forward pass of the neural network. The input goes through the first hidden layer, then second hidden layer, then third, and finally output layer. For each hidden layer, I apply a linear transformation followed by ReLU activation. The output layer stays linear because this is a regression problem. Also, instead of standard matrix multiplication, I use tf.einsum, which satisfies the assignment requirement. I also stored intermediate values because they are needed later for propagation. Next is loss function, and since this is a regression problem, I use mean squared error. And in the next code cell, what I do is, this is the important cell in this notebook. Here I manually implement back propagation using the chain rule. Starting from the loss, I compute gradient step by step for output layer, third layer, second, and the first layer. I also use the derivative of ReLU in the hidden layers. So this cell shows how the neural network learns mathematically without relying on automatic differentiation for the full training logic. Next is parameter updates. In this cell, I update the model parameters using gradient descent. After computing all gradients, I subtract the learning rate scaled gradient from each weight and bias. So this is a manual optimization step. Next, next code cell is training loop. This cell contains the training loop. For each epoch, I run the forward pass on the training data, and then I compute the training loss, run the backward pass to calculate gradient, update the weights and biases, then compute validation loss. I store both training and validation loss for every epoch so I can plot them later. This is a fully manual training loop which makes the learning process very transparent. And we can see for for each epoch, like epoch for 100, what is the training loss and what is the validation loss is for that respective epoch, and the epoch keeps happening till 700. Next is loss curve plot. In this cell, I plot the training loss and validation loss over epochs. This helps me check whether the model is learning well and whether it generalizes properly to validation data. So this is a curve that we can see, which is training versus validation loss. Next, in this cell, I define a helper function to compute the final regression matrix, and which involves MSE, RMSE, MAE and R squared. This gives a clear numerical evaluation of model performance. Next, in the final code cell, in this code cell, here I print the regression matrix for the test set. These values show how accurately the trained neural network predicts the nonlinear target. And we can see the values of RMSE, MAE and R squared respectively. And also these are the sample predictions for the input. See, if we can see, if we take this input, this is the input and how much is it true and what is the prediction of it. And also we can also see the final cell, this is the scatter plot of true values versus predicted values. If the model performs well, the point should lie close to the ideal diagonal relationship, as we can see here. So this gives a visual confirmation of the final regression performance. So to summarize this notebook, I would say I implemented a 3 hidden layer nonlinear regression neural network in manual NumPy style way. I generated synthetic data, visualized it, defined the network parameters manually, implemented forward pass and back propagation using the chain rule, trained the model and evaluated using regression metrics and prediction plots. That's it with this notebook demo. Thank you.